Uh, let's see. Yeah, basically, I'm recording today's class just because there was a new topic that I haven't mentioned before, so I'd rather have it on the video version of it, especially because the break I wasn't expecting too many people to show up today. So, well, the idea for today is just to continue talking about eigenvalues and eigenvectors. Sometime this week, I'll send you like an announcement. I'll post like, practice exams for the final and things like that. So that you have something to do if you want during the break. So I'll try to do that tomorrow, actually. And also like give you like a last grade scope assignment for you to work on. Start wrapping up, of course. Okay. So just as a quick reminder, the idea is that again, like it's not just for like 2x2 matrices, but it's easier to do the picture in that case. Let me see if I'm just checking that it's recording. Yeah. So if you have a vector and then you have a matrix in general, when you multiply the vector by that matrix, like the new vector that you get is like like kind of like in a random spot on the plane. It doesn't have like a direct relation with the original vector, but the idea of like an eigenvalue and eigenvector is that it happens occasionally that the vector that there's some vector that when you multiply them by the matrix, the new vector and the original vector are aligned, or they kind of belong to the same line. And so that's the idea of like an eigenvector. So an eigenvector was an eigenvector of square matrix A. It's important here for the matrix to be square. So square matrix A. If AB, what does it mean to say that the new vector is on the same line as the original vector? It just means that one is like a multiple of the other, like one is a rescaling of the other. So you say that AB equals the original vector times a rescaling, and this rescaling is what's called the eigenvalue. So here is lambda, that's the usual name for this, it is called like the rescaling. And it's like called the eigenvalue. Okay. And also important, kind of like a convenience for the definition is like to ask B to be non-zero, and B is different from the zero vector, because otherwise it's kind of silly, because if you put the zero vector here, it's like A times the zero vector is always the zero vector, so that kind of would work for any matrix. So A and B is not the zero vector. So again, in general, like you don't expect this to happen for any random vector that you choose. If you remember last time, we were playing with some concrete examples, and it was kind of hard to find just by eye, unless the matrix is relatively simple, while eigenvectors could be. So the idea is like it's kind of like a two-step process. Like first, how do you find the eigenvalues, and how do you find the eigenvector, and then how do you find the eigenvectors corresponding to that eigenvalue? So first, this is what I told you last time. So how do you find the eigenvalues? So what we saw is that to find the eigenvalues, you have to solve the equation. Well, the equation determinant of A minus lambda I equals 0, where I is the identity. Okay. What you'll see is that, and I will do a couple of examples in a few minutes. So what you'll see is that this is an equation that happens to be a polynomial in lambda. This will be a polynomial in lambda. This will be a polynomial equation. What does that mean? Like, just in case you haven't thought about too much about this. Like, if, for example, in the 2 by 2 case, so for n equals 2 for a 2 by 2 matrix, it is like a quadratic equation. Like, what is like a quadratic equation? Something like, maybe lambda squared plus lambda plus 1 equals 0. Something like that could be like a quadratic equation. And for like a 3 by 3 matrix, it's like a cubic equation. Or a 3 by 3 matrix. It's a cubic equation. Like the lambda cube minus, that's, I mean, just completely get like writing random thing. The square plus 3 lambda. Okay, so in general, if the matrix is 4 by 4, then the equation would start with lambda to the 4. If the matrix is 5 by 5, it starts with lambda to the 5. So that's kind of how those equations will look like. And you may or may not know this fact, but one of the nice things about polynomial equations, at least definitely, you may remember this from high school, I guess. There is like a formula for like finding the roots of a quadratic polynomial. It's like the one that involves like this, if you remember, like the square root of b squared minus 4ac, like this discriminant thing. But in general, like a quadratic polynomial would have at most 2 different roots, and a cubic kind of like something similar happens for the higher degree. So a cubic polynomial will have at most 3 roots, and a polynomial of degree 4, like something that starts with lambda to the 4, would have at most 4 roots. So in general, like this is kind of like an important fact. So here's like an important fact. For an n by n matrix, you can at most find n distinct eigenvalues. That's the most that you will ever be able to find. So for an n by n matrix, you can find at most n distinct and I don't know if you have been seeing the videos that I have posted on Canvas. We'll talk more about this after the break, I guess. Sometimes, like for example, sometimes you have like something like lambda squared plus 1 equals 0, right? That could be the equation that you get. If you try to solve this, if you remember what would happen here, you would get lambda squared equals -1, right? And well, like with ordinary numbers, there's no number whose square is negative. There is a way to solve this, like using what's called like complex numbers. But I'll probably do like a crash course on that because I'm not necessarily expecting you to remember too much of this. So like what I'm saying is that if you look at an equation like this, you would say, well, it has no solutions, but there's like kind of like, if you use complex numbers, which again, I'll tell you what that means, then you can say that the eigenvalues will be plus or minus I. And so there will be a way to do this, but like it's a little bit more complicated than what I want to spend today discussing. Yeah.
I was just wondering if you do get imaginary numbers, does that mean there's no way to like do a scalar multiplication of original vector? You always end up rotating it.
Yeah, so like right, it is a little bit murky, like the picture of what's going on here. Because yeah, then we have to talk about what happens to when you multiply by a complex number. But yeah, like in this case, multiplying this is kind of like some sort of like rotation by 90 degrees. So actually these are like the eigenvalues of the rotation matrix by 90 degrees, for example. But yeah, it won't be, it kind of like, the picture won't be 100% accurate when the eigenvalues are complex, because you strictly speaking need like more axes to draw it properly. So, but yeah, like this one, not, it's a little bit subtle, but yeah, there's some sort of like rotation going on. That's one way to think about it. But yeah, like we won't try to necessarily, once we get to that point, I'll tell you what happens there. But I'm just saying that having complex numbers kind of will allow us to find more eigenvalues than originally we would be able to, which is an advantage. In practice, like even if you don't care about complex numbers, that's like a useful thing for other things when we talk about applications. I'll let you know why this is important. But yeah, like let me put like in parentheses that we'll talk about this later, so that you don't have to worry too much about these things for today. We'll discuss complex numbers, and probably I'll maybe ask you something to watch a video on it, like a warm up. There's very little that you need to know about it for what we will use. So again, this is the first key question of for this type of problems, which is like, how do you find the eigenvalues? And again, I'll do a few examples in a second. And then once you have the eigenvalues, how do you find the eigenvectors associated to a given eigenvalue? So that's this is kind of step one, if you like. And in step two, is that once you know the eigenvalues, right? You know the eigenvalues, or let's say you know a particular eigenvalue. Maybe you once you know an eigenvalue, how do you find the corresponding eigenvectors associated to this eigenvalue? Associated to this eigenvalue. Okay. Well, so you need to solve, right? You need to solve a b equals lambda b, right? That's the definition of eigenvector. But if you remember last time, that is the same as a homogeneous system, or the homogeneous system. A minus lambda b equals 0. Sorry, minus lambda I times b equals 0. So if you remember, whenever we had like a homogeneous system, that was being called a null space. So in practice, to find eigenvectors, what we will do is compute null spaces. So what we will do, we will compute. In fact, we'll do something more specific. We'll find a basis for the null space. So we'll find a basis for the null space of this matrix. And then the eigenvectors will be the linear combinations of the basis for this null space. So the eigenvectors will be the linear combination of the of these basis vectors. I mean, with the exception of the vector zero, because we're kind of excluding the vector zero from the definition, so they do not yield zero. But basically, like, once you have the basis, you more or less can take any linear combination that you want that will give you an eigenvector. The only linear combinations that are not allowed are those that would produce a zero vector. But it's not like, in practice, you just give the basis and then you're good to go. Like, so like understanding the basis is more or less for most of the linear algebra questions, whenever there's a vector space lurking around, like understanding finding the basis, it is what you're after. And after that, everything else is okay. Okay, so let me give you a few examples how to find eigenvalues and eigenvectors in slightly more complicated matrices like 3x3, 4x4, and then I'll give you like an application of these to graphs, which is kind of fun, so that you see like how they can kind of appear in different contexts. So let me see, what should I write? Okay, so I'll just write like the two things that we have to do here so that I can refer to them. So the first thing that we'll do in general is that the determinant of A minus lambda I should be zero. And the second thing that we have to do is the null space. So we have to find, we need a basis for the null space. Okay, so these are the two things to keep an eye on for these problems. Okay, so I think I can put erasing here. Yep. I mean, in practice, kind of like the most that you'll see is like 3x3, even. Yeah, even 4x4, but if it's 4x4, it's kind of very simple. You know what I mean? Like you'll see actually the 4x4 that I'll do, because like, finding like the thing is like I mean, there is like a formula. The problem is like to find the eigenvalues, you kind of have to find the roots of an equation or the roots of a polynomial. That is not super easy to do unless it's 2x2. So usually if I give you something that's like a bigger matrix, is because there's like a lot of things that you can factorize so that like the problem becomes relatively simple. You'll see what I mean with the two examples that I'll do now. But yeah, in practice, like most of the examples I care about are kind of 2x2, and then there you'll see like the occasional 3x3, 4x4 matrix.
Okay. I also noticed that for the quadratic is n the square plus lambda plus 1, but for the 3x3 it's 3 then. Is that
Oh, right. Well, okay. So like the particular numbers here are completely random. The thing that mattered here was that for the 2x2, it will always start like with lambda squared, and for the 3x3 it would always start with lambda cubed, and if it's 4x4, it will start with lambda to the 4, and so on. What comes after that is just like I was writing random numbers. But what's important is that if size n by n, it starts with lambda to the n. So meaning that the degree of the polynomial is the same as the size of the matrix, if that makes sense.
last thing is what is the second one because has a plus 1?
Oh, okay. Is that that's a good question. Like the homogeneity is not if I could like this is not even like a linear equation, right? Because it has a lambda squared. So the when I say about something being homogeneous, I mean what's homogeneous is the system of equations for the eigenvector. The eigenvalue is a completely different equation. Like, we don't even care about necessarily calling it homogeneous or not, because as you say, like, it's really not even, it wouldn't qualify as homogeneous under our definition, but even also because it's not even like a linear equation, you know what I mean? So yeah, like finding the eigenvalue is kind of outside linear algebra because it involves equations which are not linear. So you'll see that in a second. What's still linear algebra is how do you find the eigenvectors? If that makes sense. But yeah, no, I see what you're saying. Yeah, it can be a bit confusing. So In practice, it doesn't cause that much confusion, but yeah, you'll see in these examples. But it's important to notice that yeah, these equations for the eigenvalues are quadratic or cubic or quartic or quintic, whatever like the degree of the matrix, the size of the matrix is. So, but good. So yeah, let me do a 3 by 3 example, then I'll do a 4 by 4, and then I'll give you an application to this graph stuff. So. And yeah, next, after the break, we'll talk about other applications about eigenvalues and eigenvectors, which is really they have a lot of applications. So this is kind of where we can like, see like the fruits of the course coming in, like in terms of what we have been knowing up to this point. So let's start. Okay, if it's okay, I'll erase this part here as well. So hopefully to try to fit everything into this, like, into the single board. So let's start with this one. I give you this matrix 1 0 0 0 1 0 3 0 2. Okay, and I'll ask you for like the typical question would be like, well, what are the eigenvalues and the eigenvectors? So find the eigenvalues and the corresponding eigenvectors. Eigenvalues. So again, you have to look at the for doing the eigenvalues, you have to look at the determinant of A minus lambda I. So let's try to look at that. What does this mean? It means that you're like, lambda, like I, the identity. So you're subtracting lambda from each entry of A along the diagonal. So this is actually the determinant of. Usually you just write the same matrix minus lambda minus lambda minus lambda. This is like what always happens. So you just subtract lambda along each diagonal element. So it's 1 minus lambda 0 0 0 1 minus lambda 0 3 0 2 minus lambda because again this is A minus lambda at 1 0 0 0 1 0 0 0 1, and so this gives you the same as A minus lambda 0 0 0 lambda 0 0 0 lambda. So you see, like again, if you come to subtract the matrices, you just subtract. The only thing that's non-zero in this matrix is like the diagonal stuff. Is that making sense? Questions about this?
Yeah. You should always end up like lambda, lambda, lambda.
It will always be lambda, 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 basically, yeah. So, and if 5 by 5 is lambda, 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 you know what I mean? It's like just a bunch of full of lambdas like along the diagonal. It's very easy to work with in practice. Now, this is so you want to compute the determinant of that 3 by 3 matrix. I kind of set it up so that it is easy to find if you use some of the properties of determinant. You could even use the definition, but there's some simplifications here because this matrix has a particular form. I don't know if anyone can identify what shape this matrix has. Well, it's a triangular matrix. Is this one is called lower, but because all the non-zero stuff is on the diagonal or below. But really, you only needed to know that it's triangular. So once it's triangular, the determinant is just the product along the diagonal. So let me just put here that it's a triangular matrix. Well, you get 1 minus lambda squared times 2 minus lambda. Is that okay? And like the nice thing about doing it this way is that it's kind of already factorized for you. So you don't want to kind of expand this out and like distribute and everything. That's kind of like going the opposite direction of what you like, because this is a lot easier to understand when this becomes zero, right? When is this going to become zero? Question mark. Well, lambda has to be 1 or lambda has to be 2, right? Like those are the two options. So lambda equals 1 or lambda equals 2. So this is kind of what I meant, if the matrix is like, for example, 3 by 3 or 4 by 4, like what will happen is I usually I'll give it in a form where it's kind of like once you compute the determinant, it's very almost factorized, like if you do it like in the natural way. So so this is a 3 by 3 matrix. Again, at most we could find 3 eigenvalues, 3 distinct eigenvalues. This one happened to have just 2 eigenvalues. That's okay. So and so once you have like the eigenvalues, for each eigenvalue, you can find the corresponding or associated eigenvectors. So that's where we have to look at the null spaces. Okay, so let's find first like the eigenvectors for lambda equals 1. So again, you have to look at the null space of A minus lambda I in general, but lambda in this case is 1, so you're looking at the null space of A minus the identity. So what is that? That's a null space of 1. Well, it's like lambda equals 1, so it's essentially the same that you have here, but just putting lambda equals 1 in this matrix. It's kind of like the same matrix, but just like you're giving now like a particular value to lambda. So it's like the null space of 0, 0, 0, 0, 0, 0, 3, 0, 1. Yeah. So many times, like actually finding null spaces is pretty fast. Like there's almost no reduction needed for the matrix because like our matrices are so small. So what is a null space? Like, I mean, again, I think kind of if you want to like kind of emphasize everything again, you can. This is like homogeneous system that we would like to solve. But again, there's almost nothing here to do. Like if you wanted, you could make this first entry a 1, but it's kind of like an overkill because like it's just like a single equation. So you might as well just rewrite it as a homogeneous system. The first equation says 0 equals 0, that's not useful. 0 equals 0, which is not useful. And then the only one that kind of tells you something interesting is that 3x plus z has to be 0. Is that making sense? And so you remember how we were finding the basis for a null space. You just use the last equation because it's the only one that's interesting to solve for one of the variables. The easiest thing you can do here is just say that z equals minus 3x, right? So what that means is that if you have x, y, z, that's the same as x, y, and z is minus 3x. And then you do the same thing that we were doing before. You break the vector into the variables. So like the peak with x has is x times 1, 0, -3. And the piece with y is just y times 0, 1, 0. Then you can change the version. What does that mean? It means that first of all, it's saying that V1 and let's call this V1 and V2. I'll write it there on the top. So V1 and V2 are eigenvectors. Are eigenvectors for the eigenvalue 1. For lambda equals 1. And any other eigenvector of this eigenvalue is a linear combination of these two. That's what the claim. That's why finding a basis is kind of useful, because it allows you to describe any eigenvector for this eigenvalue in terms of these two like basic ones. And any other eigenvector for this eigenvalue. Is a linear combination of these two.
Find another item.
Better.
Because it's a really complex. Wasn't having like
So what I'm saying, okay, so kind of what I was saying is that let me try to make it more concrete. So like, if you take this matrix, right? If you take this matrix, and if you take this matrix and you multiply it by the first eigenvector, right? So if you multiply it by 0, 1, 0, -3, what you're going to find if you do the matrix product, right, is actually 1, 0, -3. You'll find the same vector. So that means that this vector was left alone, untouched, right? If you try to do the matrix multiplication, you'll see that you get the same one. And so that's why the eigenvalue is 1 here, because that means you're doing nothing to the eigenvector, to the vector, right? Like this is actually leaving it exactly as it started. So that's why this is the eigenvalue equal to 1. And the same happens, with the other one. So you would get like 0, 1, 0. If you do this like product, like I mean, it's a fun exercise to do, I guess. So if you do that, you'll see that the vector was left alone, like nothing happened to it. And so that's why you say, well, it was multiplied by 1, right? So what I'm saying is that, for example, what is a linear combination of these two? A linear combination of these two vectors would be adding them together, right? If you take these two vectors, what is a linear combination? Any kind of like sum between them. So let's say if you add them together, let me write this. So if you add them together, what do you get if you add them together? You get 1, 1, -3, right? And I'm saying if you do that product, right? These will also give you 1, 1, -3. So it's still the same eigenvalue. But it didn't have to be just the sum. You could have done 3 times this one plus 7 times this one. You get a new vector, you multiply it by the matrix, and it leaves it untouched. So the idea is that once you have like the 2 basic ones, you just add them however you want, and that's why that's how you end up getting all the eigenvectors corresponding to this eigenvalue.
so basically you can check this. Our solution is the eigen.
Yeah, if you want, you can check that is an eigenvector by doing the actual multiplication.
By the eigenvector that we have.
Correct. Yes. If you want to verify, you can verify like that way. Is that making sense? So yeah, so this one was like B1 plus B2. And what I'm saying here is that any vector that kind of gets left alone, it is just a sum of these two vectors. That's the whole point of finding the basis. That's the idea of like finding the basis for kind of associated to this eigenvalue. And then we're not done yet, right? Because we still have like another eigenvalue that we have to work with. So I think I still have room here. So let's do the eigenvectors for, what was the other eigen, two? Good, thanks. So, what are the eigenvectors? For lambda equals 2. Oh, you have to look at the null space of A minus lambda I. That's the null space of A minus 2I now, because lambda is 2. So you subtract 2 from the diagonal of the matrix. You subtract two from each of the diagonal elements. So you're looking at the null space of -1, 0, 0, 0, -1, 0. Okay, and then 3, 0, 0, right? Okay, so let's see what happens here. So this one, again, most of the time these are pretty easy to solve. So it's almost there's almost no need to reduce the matrix, for these problems, actually. But at least to do something like, let's say I'll do 3 row 1 plus row 3. But again, -1, 0, 0. Okay, and this is again a very simple homogeneous system. You get well, like you get negative x equals 0, negative y equals 0, and 0 equals 0. Or another way of saying is that x has to be. So what does that tell you? Tell you that x has to be 0 and y has to be 0, right? Right. So if you take any vector x, y, z that's in the null space, you know that you're forcing the first two entries to be 0. So any vector in the null space is a multiple of 0, 0, 1. Okay, so I guess I can write it here. So what that means is that if you call this V3, because you already used V1 and V2 there, so V3 0, 0, 1 is an eigenvector. And for lambda equals 2. And any other eigenvector is a multiple. Other eigenvector for this eigenvalue. For this eigenvalue is a multiple of V3. And so kind of coming back to this idea of checking what happens here, what I'm trying to say is that if you take the matrix A, what does it mean for this to be an eigenvector? It means that if you take the matrix A, sorry, the matrix A originally would be, it was, it's that one. You see, if you take the matrix A and you multiply it by 0, 0, 1, it's an easy product to do because there are a bunch of zeros. So like the only thing that you end up getting is 0, 0, 2, but that is 2 times, you see, it's 2 times the vector 0, 0, 1. I'm going to put this knowledge. So you see, what this is saying is that if you take this eigenvector, you multiply with the matrix, the vector that it spits out is just 2 times the vector that you put in here. That's why the eigenvalue here is 2, because it doubled it in size. Whereas in the other cases, it was not doing anything to them, so that's why the rescaling was just 1. Okay, so wait, yes, it's E3.
2 times 0, 0, 1, or just 0, 0, 1?
Sorry, V3 is just 0, 0, 1. What I'm saying is that if you do the product, you get 0, 0, 2, but that's 2 times 0, 0, 1. So that's 2 times V3. So what I'm saying is that you know, A times V3 A times B3, which is this, comes out to be twice B3. So that's it's just saying like you double inside the vector B3. Yeah. And any other vector that the matrix will double for this particular matrix, any other vector that was doubled by the matrix is a multiple of 0, 0, 1. That's the whole point of saying that this is like a basis for the null for that particular null space. So if you have any other vector that was doubled in size, it had to be a multiple of 0, 0, 1. So that's kind of what the like about the eigenvector is being saying. Does that make sense? Okay, let me do let me do a second. Okay, let me do an example with 4x4, and then I'll give you like an application of this stuff. So let me see. You know, kind of, if you haven't thought about this, it's kind of like an unexpected place where these eigenvectors pop, kind of show up. So that's kind of what makes it interesting. So yeah, like just to do a quick one. So then you see like it really works for any squared matrix. Is that obviously the calculations become more tedious as we move along. So let's do it. Let's put it here. So, well, okay, so I forgot to say this, I'll say next time after the break. So we found like, for the first eigenvalue, we found two basis the basis consisted of two vectors, and then this one has a single vector, 2 + 1 = 3, and this is a 3 by 3 matrix. And then there will be something called a matrix being diagonalizable, which requires then being like as many linearly independent eigenvectors as they are like as the size of the matrix. And for a 3 by 3, that will mean that you needed 3 linearly independent eigenvectors, and but then we'll say that this matrix was diagonalizable. But again, we'll talk about that next week. And that's really diagonalizing. Talking about diagonalizable matrices is one of the most important topics of linear algebra, because it allows you to do a lot of like interesting things with them in a very direct way, like defining the exponential of a matrix, the square root of a matrix when it exists, like with some conditions. But all those, like, yeah, I'll tell you how those do all those things work next time. So here, let's do the same, find eigenvalues, eigenvectors. Oh yeah, sorry.
You said that I can.
Independent. We'll see that next time. Yeah, they when the eigenvectors come from different eigenvalues, they are automatically independent. And so the three together will all be linearly independent.
So V1 and V2 are still linear independent?
They are still linearly independent, yes. Because they were a basis, so the fact that they made up a basis kind of made them automatically linearly independent. So you have like these two, yeah, it's kind of like you have two backs, you have these two that come from the first back and another one that comes from the second back. Whenever you choose from different backs, like they're always independent. And then if you choose from the same back, they're independent in this case because they were a basis. So that's kind of what made them independent to begin with. But yeah, what we'll see next time is that you can kind of use these three to create like some sort of like overall basis for all the vectors of size 3, and that will be related to this diagonalizability stuff. But yeah, sure. Okay, so kind of the same. How would you find the eigenvalues for this matrix? Let me erase somewhere in here. It is so you have to look at the determinant of A minus lambda I, right? And that's a determinant of again, it's just subtracting lambda from the main diagonal, so it's a determinant of 2 minus lambda, 1 0 0 0 2 minus lambda, 1 0 0 0 2 minus lambda. 0 0 0 0 2 minus lambda. And there's something similar that happens here, that allows you to compute the determinant pretty easily like last time. So what's the thing that you can say again? In this case, that is upper triangular. But again, the only thing that matters is that it's triangular, either upper or lower. So like this is like a triangular matrix. So you get 2 minus lambda to the 4, which again means if you were to expand this out, you would get something that starts like with lambda to the 4, basically. And you want to know when that is equal to 0. When it is equal to 0, well, there's only one case here, lambda equals 2. So there's actually only one eigenvalue for this matrix. Okay. And what is the corresponding eigenvector? Or what are the corresponding eigenvectors, I should say? Okay, you look at the null space of A minus lambda I, the null space of A minus 2I. Okay. And it's just subtracting 2 or plugging in lambda equals 2 here, so you get the null space of 0 1 0 0 0 0 1 0 0 0 0 0 0 0 0 0. I mean, this is like a very easy null space because there's actually nothing to reduce. Like, so it just gives you that y equals 0, that z equals 0, and the last two equations like are vacuous, like they just say that 0 equals 0 and 0 equals 0. So if you take a vector, which was X, Y, Z, W. You're saying that Y and Z are 0, so you get X, 0, 0, W. Okay, and this is X times 1, 0, 0, 0 plus W 0, 0, 0, 1. So in this case, the basis consists of two eigenvectors, which again you can call them V1, V1, V2. So the basis consists of V1 and V2. And any other eigenvector for would be a linear combination of these two. So, I'll refer to these two matrices that we just used after the break. So I'll remind you next time what they would look like. It is first like to show you that even if it's 4x4, depending on how simple it is, like actually this can be easier than even the 3x3 matrix. So like the size is not necessarily like an indication of how complicated or how much time it would take you to solve the problem, because this one actually was faster than the previous one. But yeah, like what will be important next time is that this is a 4x4 matrix, but you're kind of only able to find two linearly independent eigenvectors. So we'll see next time, we'll say that this matrix is not diagonalizable. What's that? Explain what I mean by that.
The matrix isn't upper triangular, it's just a regular matrix.
Yeah, it's
more difficult then.
it can still be done. It's just that it's just that there like you get like a mess and then you do need to factorize it. So you have to be kind of lucky that like factorizing the polynomial is relatively easy. But if I give you something 3x3 or 4x4, which is not triangular, it will have something at least where you can always factorize like a lambda or lambda squared, because otherwise I don't want you kind of to waste too much in the the algebra of like factorizing polynomials. That is kind of like more like the concept. But yeah, it can be done if it's not triangular. It's just that then you get like you would get something like, if it's not triangular, then you won't get anything that kind of comes so easily factorized. So you get like something like lambda squared, like lambda to the 4 plus 3 lambda cubed plus 2 lambda squared plus lambda plus 5, something like that. And then how do you, of course you can set that equal to 0 theoretically, but it's not necessarily super clear, how you would actually solve the values. You know what I mean? So in practice, what I'm saying is like, if I give you something like this, it's maybe more like this, where you can then pull out the lambda square and then you have a quadratic thing that you can then factorize, because the point for me is kind of like to give you something where you can actually find the roots like quickly. You know what I mean? Yeah.
Is it possible, like for a n by n matrix, that we could find more than n bases? Is not possible.
No, it will not be possible. Yeah, I'll give you those properties next time but yeah, the most you cannot find more than n linearly independent eigenvectors.
So like at most n bases can be.
At most if it says n by n, yes, at most a basis of n eigenvectors can be found. And when it's precisely n, that's when you will say that it's diagonalizable. So this one falls short because it needed two more. But what I'm saying is, in a 4x4, you could never find like 6 linearly independent eigenvectors. It's kind of like the most you can get, the most you can reach is like 4 for a 4x4 first. Is that okay? Any other questions on this? Okay, let me give you a quick application of this stuff because I think it's kind of fun. So I just need you to say something quickly about probabilities. So when people say probability, like you would say something like, probability that there will be rain tomorrow is 50% or 25%, or like what's the probability that someone, will win the lottery, right? So many times, like, probabilities are just given in terms of percentages, it's kind of easy to turn them into numbers between 0 and 1. That's more convenient for a mathematician. So like, if you say 50%, what does that mean? You can think about it as 50 over 100, right? Which is 1/2, right? Or 0.5. And same with 10% or any other number that you want, right? Like that would be 0.1. So any probability, a probability or a number that you give as a percentage, probability can be expressed as a number between 0 and 1. Number that making sense? So reasonable. Okay, so again, just clarification, because so if you say 100% chance is the number 1, and that's kind of saying with certainty, right? If something has like 100% chance of occurring, then more or less you're betting your life on it happening, right? If 0% chance, like you're claiming it's basically impossible for it to occur. So just to start with a simple example, hopefully, like, relies in some sort of like intuition that you would have. Think of having like, how did I draw this? I'm drawing them this. Okay, let's say you have these 3 nodes or circles. You can think of them as 3 websites. Okay, so there's like a very basic internet where there's only 3 websites in the world, so that's easier to understand. So ABC, and you could say, well, maybe there's in website A, there's a link to website B, right? And so I'll draw an edge, and then from website B has a link to website C, and website C has a link to website A, right? So you have a very simple, what's called like a graph. So basically, it's kind of like, each website is like, if you think about it, like in this clockwise, each website is referring to the one that appears in the clockwise order, right? So imagine like, okay, so what would happen here? Like, imagine that you like log in on the website, on the internet, and then like you are like, okay, I'll just start with website A and read through it, but then I'll always, at the end of the day, I'll just press the link to the next website, and then that will take you to B, and then once you do that for B, it will take you to C, and once you do that for C, it will take you to A, right? So it's kind of like an eternal thing, like it would always move from A to B to C, from A to B to C, and so on. So it kind of makes sense that you would spend kind of like equal amounts of time. I mean, it's like, imagine that you're just clicking like crazy. You don't even read the text. So you, like the moment you log in into a website, you just press click to the next one. So it seems like it kind of makes reasonable in this case, like if you don't know anything else about the situation, to say that you spend the same amount of time on each website, right? Is that okay? So you would like to say that, if you were to rank these websites, and that's kind of like how the Google, I mean, it's kind of like a baby version of how the Google ranking works. So if you were to rank these websites, you would like, there's not really like a good way to distinguish them rank wise, because they are kind of spending the same amount of time on each of them. Or kind of, or another way of saying it is like, think of a website being as more important if it has more links coming to it. Everyone is being referred by another website or another person, so like they're kind of all equally important. So you would like to say that each website, so in this case, each website has equal importance in some sense, right? And so, so you could think of like assigning like a probability to them, like being like, what's the probability that if I ask you on which website you are in, you say A, B, or C. So if I just give you a call and ask you, oh, on which website are you now? Like it should be equally likely that you're on either of them. So on each of them. So what should the probability be for?
Like,
Right, it's a 3, 1/3, so the probability, each one should have each one. So each one should have probability 1/3, which is like, again, 3.33.333333%, like, or 0.333333 goes forever percent, right? Is that making sense so far, so good? Okay, now there is a matrix you can assign to this graph. So this is like the first thing you have to think about. For that, it's a little bit better to have like a different perspective on the graph. So let me put like let me represent the graph this way now. So you can say, well, there was like a link from A to B, so I'll draw it this way. And then there's a link from B to C, so I'll draw an edge like this. And then there's like a link from C to A, so I'll draw this. Right, and that kind of encodes the same information as the original graph. It's a little bit maybe kind of looks like it takes more space, but it organizes like more like as a table what's going on, because then you can say, well, there are 3 nodes or 3 websites, 3 cities also, if you want to think about it as maps and roads. So 3 by 3 is 9. So let's create like a 3 by 3 matrix. So you create like a 3 by 3 matrix. Okay. And so what are you going to put here? Like, let me put like A, B, C. B, C. Okay. And so because there's like you have to create like a convention of how you put the entries, but I'll say like, because there's like a link from A to B, I'll put there's a link from A to B, so I'll put a 1 here. Because there's a link from B to C, I'll put a 1 here. And because there's a link from C to A, I'll put a 1 here. So is that clear how I'll do another example, see if we are all on the same page on how I'm drawing the numbers. So I'm just putting like here, I'm telling you where I'm starting and this is where I'm ending. So I'm starting at A and I finish at B, A to B, so I'm putting a 1 here. I'm starting at B and I'm ending at C, so I'm putting a 1 here, and I'm starting at C and ending at A, and I'm putting a 1 here. Is that okay? And I'll put zeros elsewhere because like there's no links. So there's no sub-reference allowed, if you're Rutgers, you're not gonna put a link to Rutgers itself, like, so that's why along the diagonals, we would always have zeros. I mean, obviously there are modifications you can do to all this setup, right? So let me just do a little, slightly more, I'll still haven't finished the example, but like just to see we're all on the same page about how these links are supposed to work and the matrix that you come to it. Let's do another one. So like imagine, it's not, it's just a slight complication, but I still have A, B, C. So A will only lead to B, right? B will only link to C, but C likes A and B equally. So it has a link coming from one of those. So once you get to C, you can either go to A, or there's also will be a link to B. So maybe they're mutual friends, right? That's how networks work. So you will reference each other. Okay. So again, hopefully the arrows are visible. We have to distinguish the arrows. So again, there's a matrix associated to this problem, but let's just break it into like column version. Yeah.
First, the reason that you use it was C to A instead of like the first one being A to B, like first.
No, there's actually different conventions. It's like it would be the transpose.
Yeah.
Yeah. No, just because I'm following the ones that I was reading the other night. So no, but you can find the other conventions as well. So yeah. Actually, the other convention is more used in other places, but I was like, I just wanted to copy paste the examples without making any modifications being lazy. So yeah, but I mean, the point is like once you make a convention, just stick to it, be consistent, and then you're good to go. But yeah, like the other one would just give you the transpose, basically. That's So. Okay. So what is in this diagram? From A, you're going to B, right? And then from B, right? From B, you're still going to C. But C, oh my God, let me do this a bit bigger. But C now has two options, right? So now C can go to A or it can go to B, right? That's kind of how it's looking like. Okay. So the first, okay. So there's like a matrix that you can create here, right? Let's call this matrices M for matrix. Nothing, not any particular meaning to the letter I'm choosing here. So again, it's kind of A, B, C, A, B, C. Okay. And so from A to B, there's a path, right? From B to C, there's a path. And then from C, there are two possible options. So you can go, you can go from C to A, or you can go from C to B. So you can put it like this, right? And that's what you end up getting. Is that making sense? So far, so good, everyone on the same page? I just wanted to have like a second one, which was slightly more complicated, so that you would see how to construct it. So here, like I'm going to tell you in a second how we're going to think about this problem, but you can say, okay, so imagine that you have these three websites, and again, you're kind of like clicking like crazy. And so now you ask your friend, oh, on which website are you on, right? So you could ask, well, what's the probability, that you're on A, or what's the probability that you're on B, or what's the probability that you're on C? Or another way to ask this is like, what fraction of the time of your time you would spend on each of them? Or another way to ask it, which is kind of more like in the spirit of like how this Google things would work, is how would you rank these websites in importance, right? So it's kind of clear, at least, that it cannot be the case now that they're all equally important, because of this splitting that C has. So you have to think about this in a slightly different way. But the first thing that I'll do, is that we have this matrix, but let's do another matrix, which is called P for probability, which is just telling you the probability, that if you are in one of these websites, you'll go to the other website. So if you're an A, since there's only one possibility that you have, you would certainly go to that one, right? So I'll put a probability 1 for 100% certainty. If you're at B, it's gonna be A, B, C, A, B, C. If you're at B, with certainty you go to C. So I'll put 1 here. Now it's for probability. But if you're at C, you can go either to A and B. And if you don't know anything about the problem, the easiest thing to do is kind of like you're rolling a coin, sorry, because I only have two options. So you're rolling a coin and wherever it lands, like that's where you would go next. So it's 50-50, and 50 is 1/2. So you get 1/2 and 1/2. Okay, so it's basically the same as the previous matrix, is that now I'm taking all the numbers be between 0 and 1. So like in this column, these add up to 2, these two numbers add to 2. So I kind of like divided by 2 to make it a probability. So this is like now. Okay. That making sense. So more okay. So just to kind of moving more in the direction of how is it related to eigenvectors. So at least now you see that there are matrices in all of these graphs, right? So if a website has like how many websites are they say it's like 10 billion websites, or there could be more like websites on the internet. I don't even know. Like then it's a 10 billion times 10 billion matrix that describes all the internet. All the links between websites, and it would be a lot more complicated because when websites would reference it themselves, and maybe there's a sense in which you want to count multiple links from one website to the other. So it's obviously like a very complicated problem, but like this is very basic. So one way to think about But the idea of like these ranking systems is that so at first approximation, you want to think, well, how should you rank the websites depending on how many other websites are referring to you. So let's, if you call like X that how important A is, and Y how important B is, and Z how important C is. So what happens like is that for the, for the first graph, for the first system, you would like to say, well, I mean, it's actually better to say it here. You would like to say, well, A should be at least as important as C because there's only one reference to A coming from C. So you would like to say that the importance of A is the same as the importance of C. And for the second one, you would like to say, well, the importance of B should be the same as the importance of A. So you like to say something like this. And for the last one, you would like to say that the importance of Z should be the same as the importance of B. Okay. Which is a very simple system of equations to solve. But if you, like, again, it kind of looks like an overkill in this case. You can write this into matrix notation. So what would be the equation here? 0, 0, 1, 1, 0, 0, 0, 1. Right, so if you do, like, maybe it's worth taking a second to check this. If you do this times this, if you do this times this, you get C. If you do this one times this one, you get X. And if you do this one times this one, you get Y. Right, so this is a matrix, right? This is a vector. This is a vector, so you're the same vector, so you're looking for C equals AB. So what is that? We just saw this, right? What is that? When you're trying to find a vector that equals a matrix times that vector, so what is that? Starting with the word
Identity.
well, it's not the identity per se, because depends on what you mean by that, because it's not the identity matrix here. It's like an eigenvector for this matrix, right? Where the eigenvalue is just 1. So this is again, so it's just saying that V has to be an eigenvector. It's an eigenvector of A with the eigenvalue 1, if you think about that. Of A with eigenvalue 1. Why? Because if you remember what is like an eigenvector equation, it's like A times B equals lambda B. Right, but if lambda happens to be 1, there's nothing being done to the vector, so it's just A B equals B. And lambda equals 1. Is that making sense? So what it's actually saying, this is actually saying that something in the system is actually finding the same as finding an eigenvector for this matrix. And you can find, you can show, let me put it as like a thing that you can try to do. You can show that an eigenvector, let me write it as an exercise. So show that B equals 1/3, 1/3, 1/3 is an eigenvector of that matrix. Okay, so maybe let me do it for the other one because this could be a little bit too confusing because this matrix is more or less, there's almost like nothing really going on there. So let me explain it, let me try to do it here. Okay, so yeah, I'm going to rewrite, I'm almost done. So I'm going to rewrite this ABC. What I'm saying is that there's one from A to B. You know, there's one link from A to B, there's another link from B to C, and then a link from C to B and C to A. Okay, so again, think of X, Y, and Z as the rankings or how important X, Y, and Z are. So what they're saying is like how important X is. Well, all X is, let me put it inside each circle. X is how important A, I mean, this is asking how much should we value the website A? Well, all your value is just coming from C because that's the only one that's referring to you. But kind of like C's worth is being split among two websites. So like instead of putting the X equals Z, I'll just put X equals Z over 2 because how much you value this website is just half of your total amount of value. Okay, and then how much is Y being valued? Well, Y is receiving all of X's affection or words, like, it's being referred exclusively. This is like the only one that X is referring to. But also you're getting the word or you're getting the validation from website C, but how much validation? Half of what C has to offer. So let's put this C over 2. Okay, and how much validation or how much value this website is receiving? Well, all its value is coming from the reference from the website B. So in this case, but B only refers to one website, so it's getting all the attention from the second website. So now, okay, this looks like a better system of equations actually. So if you think about it this way, it's X, Y, Z equals what? Maybe you're more used to a more complicated system. It's 0, 0, 1 half, 1, 0, 1 half, 0, 1, 0. That's like, you see, if you do this matrix times this vector, you get these entries. But what is this matrix? It's a probability matrix.
Like 1 4 is not 4.
Oh, it's like close to that, but it's not there are no 1/4 here. So, but I'm just saying that you see, like this is still an eigenvector equation for one matrix, the matrix P. So you're finding an eigenvector. So you're trying to find an eigenvector for this matrix. So the goal is to find an eigenvector and almost eigenvector for P with eigenvalue 1. And it's kind of non-intuitive, maybe, but you can check if you want. I mean, you can do it by hand or you can check it with like the methods that I already gave you. You can check that if you do 1/5, 2/5, 2/5, then that is an eigenvalue 1. So that means that on average, you spend 20% of the time on website A, and you would spend like the same amount of time on websites B and C, which is not super obvious, maybe based on how the graph is designed. So, but that kind of tells you, like, it's kind of like a unexpected place where the eigenvectors appear. So, like in this case, just to summarize, like the point is that the eigenvector, the entries of the eigenvector are kind of like the relative amount of time you spend on each website, basically. So that's kind of like the first step into how like this ranking of websites work. Obviously, there are much more technicalities that you have to figure out, but it's kind of like a toy model, of how this is supposed to work. So yeah, try to take this matrix and try to check that this is actually. Do it do not cheat because I already wrote it for you, right? So you could obviously check very easily by just doing the product that this works, but just trying to do it by hand with the null space stuff, that would be like an eigenvector. So yeah, I think I should finish. So I'm doing the break. I'll post a video for this class because this I cannot mention before in the videos. So yeah, I'll send you some announcements next this week later. So.